Ready?
Yes.
So our next talk is by Amanda Montejano from the UNAM in Mexico, and she will tell us about zero-sum squares in bounded discrepancy +-1 matrices.
So thank you. I'm not happy for not being in Buenos Aires, but I'm happy for being here and could share some mathematics with you. So thanks to the organizers, Florian and Claude, for organizing this special session. I will talk about these zero-sum squares in bounded discrepancy matrices, binary matrices with entries in -1 and 1. This is a joint work with Alma Arevalo and Edgardo Roldán Pensado, both from Mexico. So sorry, how is it? Right. I will divide the talk into 3 parts. First of all, I want to tell you like the story of this project, and therefore I will talk a little bit about a problem called the Ericsson matrices problem, which is a canonical or a prototype problem in the setting of Ramsey theory. Then I will tell you about some variants of the theory that I have worked on in the recent years and that I really like. And again, as Antonio, I don't assume that everybody in the audience knows about this topic, so I will be starting basic, and I will not get into technical details. I want to emphasize the philosophy of the theory, and I want to contrast the difference and similitudes between the classical Ramsey theory in this setting and the variants that I work on or that I really like. After that, I will come back to the particular problem that we attacked and present the result that we get. So I will start with these 2 definitions. An Ericsson matrix is just a square binary matrix that contains no constant squares. A squares is a submatrix, 2 times 2 submatrix of this form, and it is constant if all its entries have the same value. So here you have an example. Binary means we have entries 0 and 1. This is a square which is not constant. This is another square which is again not constant. So maybe this matrix is an Ericsson matrix. We have to check all squares here, but as you can see here, this is a square which is a constant square, and therefore this matrix is not an Ericsson matrix. Once we saw a definition, of course we want to see an example. I can show you here a small one. This 3 times by 3 matrix is an Ericsson matrix. You can check it. And the question, the problem, the Ericsson matrix problem is how large can an Ericsson matrix be? So can you build a bigger Ericsson matrix? Here is an 8 times 8 Ericsson matrix. So you can check there are no constant squares here. And the question is that, no, how large can we go? If you know a little, so this problem was posed by Martin Ericsson in his book, Introduction to Combinatorics. And if you know a little bit about Ramsey theory, you can recognize this problem as a typical Ramsey type problem. And if you know a little bit more about Ramsey theory, you maybe know that the answer to this question is not arbitrarily large. This is a consequence of a classical theorem in Ramsey theory called the Galay's theorem. And anyway, already Erickson himself knew that the answer is not arbitrarily large. He proposed as an exercise in his book that an Erickson matrix can be greater than this huge number. No, you can, if you the size of an Erickson matrix needs to be smaller than this huge upper bound. So as I told you, this can be stated in a coloring setting, in a coloring language, which is the most common to found in Ramsey theory. So instead of thinking on this as a binary matrix, you can think this just as a two coloring of a grid, finite grid, and then rephrasing the problem, you have a square matrix, and a binary matrix is a two coloring of the grid, and then a constant square is just a monochromatic square. And there is in Ramsey theory, we have the Ramsey type parameters for each problem, for each setting. In this case, I denoted this parameter with like this, and this is the minimum positive integer, such that every true coloring, or if you want, every binary matrix of this size contains, larger than this, contains a monochromatic square, or in the other language, a constant square. So the Erickson matrix problem is to determine this precise parameter, which is now the minimal, the exact value. And in Ramsey theory, to determine those parameters precisely is very hard in most of the problems. So I will tell you the story about this parameter, the solution of the problem, because now we know how the precise value of this parameter. In 2008, best, lower, and upper bound were by Maria Ksesnovich and Jacob Manske, were 13, and again a very large upper bound, not as large as the exercise from Erickson, but depending on the van der Waals number, which is the Ramsey type parameter for the problem in integer intervals, considering two colors and arithmetic progressions with 8 terms. This value, for instance, is not known, but there are bounds. So that was the best upper bound, and best lower bound were 13. This is a picture from the paper. This is an Erickson matrix with length size 12, and after this, 2 years after, it was very surprised that the precise value for the parameter is 15. This was a result by Becker and Shalom Eliyahu. Actually, I know about the problem by Shalom Eliyahu in a conference in Seville some years ago. So they were able to prove that the exact value is 15. This is a picture of the paper. This is an example of an Erickson matrix with 14 by 14, and they were able to prove that there is no possibility to have for having an Erickson matrix greater than 15. So this was a kind of a surprise. The paper is beautiful. They use assistant computing, but also very clever arguments in order to classify these matrices. So I really like the problem. and thought, well, I'm used to work in some variants of the Ramsey theory, named the anti-Ramsey theory and the zero-sum Ramsey theory more recently. So I thought, oh, maybe I can study the same problem, same setting with these variants. So let me tell you how this goes. So in Ramsey theory, you have a mathematical universe wherever you want, and you will consider all the colorings. The number of colors it could be more than 2, and a coloring is just a mapping from the universe to a set of finite colors. Or if you can, you can see a coloring as a partition of the universe in different sets, which are called the color classes. So Ramsey theory studied the existence of monochromatic subsets where you choose a substructure of the universe that you are interested in. You want to prove that if the universe is large enough, then you can always find your structure inside one of the color classes. In the anti-Ramsey setting, instead of looking for monochromatic subsets, you look for rainbow subsets, which are structures or subsets that are transversal to the coloring. That is, they have one element in each color class and touch all color classes. So this is a very interesting setting where I have worked on a lot. But there is another one which is somehow in between, or which relates with both, which is called zero-sum Ramsey theory. And there, the point is that we have we need to add to the set of colors some addition structure, or in other words, you think on the colors as a group, an additive group, or a subset of an additive group, in order to be able to add the colors and to say which subsets are zero-sum in the group. In this setting, there is many theory developed here, mostly when the group is the cyclic group, or it has some torsion. Then there are similitudes with the Ramsey theory, in the sense that we can find somehow results analogous to the classical Ramsey theory. The whole area growing from the Erdős, Binsbund, and Sieve theorem, or the Davenport constants, etc. But when the group has no torsion, then there is no hope to have results analogous as in Ramsey theory. But the point is that they are somehow, or in some sense, similar to the anti-Ramsey theory, because in order to guarantee the zero-sum subsets in this case, when the group has no torsion, then you need to ask the coloring, or you need to put some restriction in the coloring, having some density in the color classes. So there is a connection here that we saw, and we say, oh, let's maybe we can use our tools here to prove things in zero-sum Ramsey theory over some groups that was not very studied. For instance, consider just the set of integers. Of course, as I told you, you need to, we always work with finite universes, and so it makes sense to restrict the range to some set of integers. Of course, we need some negative and some positive, and also we need to restrict the whole well, we can call this discrepancy, or to measure somehow color classes, the sizes of the color classes. You want to be them not too small. So in a particular case, we found very interesting to study just this range, just this case. So we will have colorings or partition into two classes, which are going to be -1 and 1. And then, as I told you, the frequency of the coloring is just the absolute value of the sum of all values for the elements in the universe. So this is just the deviation from -1s or 1s. And there, it makes sense to ask the following question. If the discrepancy is bounded, does this implies that we can find bounded or even zero-sum substructures in every coloring with some restriction? For instance, this is a very natural setting where the universe is a set of integers, and the typical structure to study is the arithmetic progressions, as in Van der Waals theorem. We study this problem in this setting. It happens that the answer to this question is yes. Yes, if you have for any chain of pluses or minuses, as you want to see, provided that the whole discrepancy is bounded, then you can find an arithmetic, zero-sum arithmetic progression. And we prove this I proved this with my colleagues Jerry Caro and Adriana Hansberg, I think I have to run a little bit. So we work with blocks instead of arithmetic progressions, and we manage all the parameters that we could manage. That is the length of the block, the boundedness in the whole universe, and the boundedness in the block that you will find. And our result is tight in all sense. And we also characterize the sequences that are extremal. But anyway, the techniques that we use to prove this theorem were interpolation techniques, in the sense that since you are working with blocks, you can how do you say, have the blocks like one after another, and by an interpolations arguments, we have control of the discrepancy of the blocks. So that give me the entrance to came back to my problem of this talk, which is the matrices. So if you think a little bit of the problem, is quite close to it's like a two-dimensional case of the block case, just that here we are, in this case, we are only consider squares. But anyway, the interpolation arguments are the same, and we can work again with those tools. So we started, so the problem is now clear. We started to explore the question. The main question at the beginning was, it is true that every sufficiently large bounded discrepancy matrix contains a zero-sum square? So we didn't know. So we started to explore examples. First of all, we need to know what bounded discrepancy should mean. We soon came up with this example that can be generalized, which has roughly discrepancy roughly n²/2. So we need to go smaller in order to have some theorem. So we start to explore with the linear discrepancy, linear in terms of the size of the square, but some other examples came up, which we call the split or triangular examples, where the discrepancy is very easy to measure. And if you notice, those examples are as well zero-sum square free example as well as this one. So in these examples, you have no zero-sum squares. So we need to take those examples into account. We need to manage them somehow in order to prove something. And then we keep exploring with the computer, and many other examples came. And at this point of the project, I was not so positive because there were so many examples and we couldn't see how to manage with all them. But then we keep exploring, and then we observe, again with the computer assistance, that somehow the zero-sum squared samples were disappearing apart from the triangular or split case, were disappearing when we were growing. Actually, we realized that between 5 and 11, the sentence that we wanted, it was true. How do you say? Just we need to take into account these split matrices that every time are going to be there. So the conjecture was actually every matrix, binary matrix, which is not split or not triangular, with small discrepancies, small meaning this, will contain necessarily a zero-sum square. So that was an observation, that was a natural conjecture, and we were able to prove this. Actually, we prove this using the interpolation techniques. The main idea is very simple. You proceed by induction. So you have a big matrix, you split it in 4. Because your discrepancy is small, then you can find either the zero-sum square, or you can have a negative discrepancy submatrix and a positive discrepancy submatrix, and then you can walk like step by step from one to the other until you reach necessarily a zero-sum square. So that was the main idea, but in order to prove this, we need to prove actually a sentence a little bit stronger, where we manage squares and almost square matrices, and then once we have a big enough split matrix inside our big binary matrix, then we can spread the information. I mean, many values are forced with once you have a big part of a split matrix. So to finish, I want just to mention some open problems. Of course, you can work with other ranges. I mean, not just -1 and 1, but more colors or more integers, or you can work in other groups. For instance, the cyclic groups. I don't think it's already new. You can work with other shapes, but in like in Gallai's theorem, or of course larger dimensions. So we go from 1 to 2 dimensions, but specifically in the problem of squares in 2 dimensions in this grid. So we get this bound, but remember that the example, the best or worst example that we have is n²/2. So maybe we can improve here. There's a lot of room there. So like 2 months after we put our paper in archive, Tom Johnson in Oxford work on this problem. He liked the problem, and he was able to prove n squared over 4. So between n squared over 4 and n squared over 2, there we have the right magnitude now, but there is a constant that can be improved. Actually, he make a more computational experimentation and goes further than us, and he conjectured that this is really the extremal example, and this should be the right. So we could be able to improve this to n over 2, and he actually proposed a precise conjecture with precise value, and that's all. Thank you very much.